Well, thank you. Hi, everybody. Thanks for coming here for Agustinus Ribal's seminar. We've had the pleasure of having him here in our laboratory as a visiting scientist for the last 6 months, and he's been a really pleasant collaborator and a great contributor to the research that we've been doing. He comes to us from the Hasanuddin University in Indonesia. He's an associate professor in the Department of Mathematics and Physical Sciences and Natural Sciences. And he got his PhD in ocean engineering from Swinburne University with Alex Babanin as your thesis advisor, yes. The well-regarded background there for sure. And he also did a postgraduate study in Melbourne, Australia with Ian Young. So some real distinguished names in the field that he's worked with, and now he's come to work with us, and we hope that we're included similarly. So he's going to talk about a field program that we had in Monterey Bay and in North Florida. He's going to talk about the Monterey Bay component here. It's coastal land-air sea interaction experiment, ONR funded, and Augustinus has done the wave modeling associated with that. So,
thank you. All right, thank you very much, Professor Brian. Good afternoon, everyone. So I'm currently on leave from the Department of Mathematics at Hasanuddin University in Indonesia. As you can see, I'm working with him and then Milan as well, and Stefan Zieger. Stefan Zieger is one of the member of a short-term team that we are going to use in this work. So what actually we are doing in this work is, we downscale the model from the global until the Monterey Bay in California, and using the model WAVEWATCH III with two different source terms, which are ST4 and ST6. So let me talk about the outlines of my talk. So I start from the motivations why we conducted this research, and then why we select the area, and then go to the model setup, how we downscale the model, and then how we what's the input and output of the model, and also we also check the input of the wind, and then because the model will be verified using the buoy observations. So in this case, we are going to show the buoy locations and also the duration of the observations. And then the model will be validated against observations. And we also will show the computation time between two different source terms, ST4 and ST6. And then we'll show you the seasonal and monthly mean significant wave height around the Monterey Bay, and then we'll also show the wave and wind directions at the locations. And the last topic will be about swell and wind sea. So if you like surfing, then that might be very important. So how to we start from the motivation. So if you're not familiar with the model, and then, or if you are familiar, and then we know that why people need the model. And if we look at the observations at the moment, let's say for example, so far the buoys, so many buoys around the world here, and then it's not include NDBC, CD buoys, and some other buoys that have been deployed. But the main issue here is the spatial coverage. For example, here, if you are working in Indonesia, so there's no work you can find in Indonesia. There's one challenging work in Indonesia for ocean waves. And then, if you're talking about the satellites observations, well, I've been working with the satellite observations for almost 6 years. And then the issue there is spatial resolution. So if we can see here, this is the satellite altimeter track. So indeed, the resolution along that track is quite good, meaning that it's about 7 to 10 kilometers. But the thing is, the spatial between the tracks is very, very close. So that's why we need the model, because we need to assess all the location. And then why the coastal area? The WAVEWATCH 3, the main input of WAVEWATCH 3 is the wind speed, and then so the quality of the wind speed will determine the quality of the WAVEWATCH 3. And then here, wind forecast. We know that wind forecasting around the coastal area is not as accurate as the open ocean. So if the wind input is not accurate, it's not really accurate, and then we can actually assume that might be the output will be questionable. So here we are going to use the WAVEWATCH 3, and then we assess the coastal area. How actually we perform the downscaling? So we starting from the global with resolution of 50 kilometers, and then we select the area around here, and because our main target is Monterey Bay, and then we increase the resolution from 50 kilometers to 20 kilometers, and then in this area we select again here. We increase again the resolutions to about 5 kilometers. Here we have actually two options. We can keep using the regular grid, or we can go to the unstructured grid. And after some trials and also some considerations, we end up with the unstructured grid. So here is the Monterey Bay. So if you look at here, this looks black, actually the high resolution around the coastal area. So if we zoom it, and then we can actually see the resolution of the mesh is very high. The number of nodes on this grids is more than 53,000, and number of elements is more than 100,000. How actually does it work here is so the three grids here we call it the two-way nesting. So they run at once, and they can communicate by themselves. So they exchange the information, but they will exchange automatically. And then once we run there, and then we get the input for this high resolution model. So we are going to concentrate on this high resolution model. How high the resolutions? We can actually see here that the resolution here is the maximum is 2 kilometers, and then we going down to about 1 kilometer, 800 kilometers until the coastline, which is about 200 meters. So we expect a smooth transition from 2 kilometers until to 200 meters. For the bathymetry looks like this. We obtained from the Shuttle Radar Topography mission. The resolution of this bathymetry is 500 meters. So that's why they call it the SRTM 15 seconds. So this grid has been generated using Ocean Mesh 2D. The input, what's the input of the model for grid 1 and grid 2 for global, and the second nest we apply the wind and ice, and then other two grids we use only the wind. And where do we get the wind? We get it from NCAR, CFS, it used to be called CFSR, now it's CFS FP2. And then bathymetry, as I mentioned before, SRTM 15. So 15 here means 15 seconds, which is about 500 meters. The source terms, we use the ST4 and ST6, and then we also apply the reflection because we are dealing with the coastal area, so reflection is important. And also we apply the SOEX bottom frictions. What does it mean? meaning that we assume that the seafloor in Monterey Bay is sandy. And then what's the output? The output model, the main output is a significant wave height. And then we have some other outputs, including the energy flux. So if one is interested in wave energy, and then they can use the energy flux. And then one other parameter is very important, because in this case we are using the explicit scheme. So we need to, how do we determine the time steps for the model? Because talking about the numerical solutions, then we use this formula, and we firstly determine the time step for the spatial. From the spatial, we can calculate the global by taking 2 or 3 times, and then the spectral we taking from the half of the global, and the source term we take the small number. So that's how we determine time step. Then the time step here, if we violate this time step, and then the model will be unstable. Here the output, we save the output every hour, but I probably don't go to the details for this. I'll talk about the comparison between ST4 and ST6 in general. So here the two main sources of two different source terms. So the first one is ST4, and then underneath is ST6. What are the difference? The actual similarities, they are similar in swell dissipation, white cabin dissipation, but the main difference is the wind input terms. So how they perform the wind input. So if I listed three of them, the main difference is so ST6 based on the observations, meaning that the wind, in order to parameterize the wind, they use the observations, while the ST4 based on the theory. And then the drag coefficients, in ST4 they apply the linear drag coefficients, while in ST6 they apply the drag coefficient based on 1. This drag coefficient reduce the high wind speed. That's probably why ST6 underestimate the high significant wave height. So, and then for dissipation in ST6 also measured, while the ST4 is just semi-empirical. If you are not familiar with that, and then we can simply say that ST4 based on theory and ST6 based on observations. How good the wind we input on the model? We can actually see so the wind obtained from NCAR, how good they are. From the directions, they're almost very good. But for wind speed, we can see that high wind speed is underestimated by CFSR. However, that's the wind that we had. We did try other winds, but we get even worse. So this is all that we can get. Okay. Now, in order to validate the model, we need the buoy. And so, what the buoy locations? Here, what we have. So this is the Monterey Bay around here. So we have 3 different sources of observations. We get the NDBC, we get the CDIP, and then we get the CLASI and the spotter. So CLASI here meaning that the observation conducted by Brian's team under the CLASI project. So they have 3 different phases of the observations. So that's why they have CLASI 1, CLASI 2, CLASI 3, and also they have the spotter. So they also apply the spotter 1 and spotter 2 phases. If you look at the inside the bay, so unfortunately there's no NDBC buoy inside the bay, but we do have one CD buoy. Other buoys are from CLASI and spotter. What the duration of the observations? So we can see here that CD buoys span 2 years of the observations, and then also NDBC But for CLASI buoys phase 1, this is CLASI buoy phase 1 conducted in 2021 around July, and then the second phase in 2021 about in August, September, October, and then the third phase phase 3 in about August or September 2022. And then also the spotter buoy phase 1, phase 2. So this is the duration of the buoy that we use for validation later on. How do we measure the skill of the model? We use 4 different statistical parameters. We call it bias, RMSE, scatter index, and correlation coefficients. And then now we are going to show how good the model and observations. So we started from the CDIP buoys. CDIP is a Coastal Data Information Program. So on the top is the comparison between the buoy and the model using ST4, while the underneath is using ST6. If we look at details, the RMSE, they are almost the same, but for ST4 they are good in correlation coefficients and then also scatter index, while the ST6 is good in the bias. And then we look at another buoy, but for simplicity we will only show 3 different buoys. And then as you can see here that here the RMSE and bias are good for ST6, while scatter index and correlation coefficient are good for ST4. And then when we take a buoy inside the bay, we can actually see it's not really consistent. So how do we make a decision? Then we pull all the data together. So all the data from all the buoys we pull together, and then we can compare the results. And then so here we can draw the conclusion that ST4 is good in correlation coefficients and also scatter index, while the ST6 is good in RMSE and also the bias. So that's based on the CDIP buoys. Now we're going to see the NDBC buoys, how good they are. So we follow exactly the same procedure, just the different buoys. So we can actually see that they are very consistent, that RMSE for ST6 and bias are very good, while the ST4 very good for correlation coefficient and scatter index. And then so we do the same other buoys, and also we follow again the procedure that we pull all the data together, and we can see that they are very consistent using the NDBC buoy and the CDIP buoys. They are very consistent that RMSE and bias are very good for ST6, while ST4 is good for correlation coefficient and the scatter index, meaning that the high correlation coefficients and small scatter index. Now we'll see. Now we can see the CLASI buoys. So how good the model with the CLASI observations. We perform the same procedure, and then surprisingly here that they have very good RMSE, but very low also correlation coefficients. So if we look at the other buoys, they are all similar, and then when we pull again the data together, and then we can compare and we can get the same conclusions, similar conclusion with the previous cases with the using the CDIP buoys and also NDBC buoys. And then we do the other observation from the CLASI phase 2, and we also get the same conclusions, and also the phase 3. So all these more than 30 observations points shows that the same conclusions, where ST6 are very good. It's very good for RMSE and bias, while the ST4 is very good for correlation function and scattering nets. So this is makes us confidence that the model does the model doesn't doesn't have any contradictions, meaning that we don't we believe that the model runs well. Now what about the spotter? Unfortunately for this model, these comparisons, we only do for ST4 because once we finish the ST6 and then I know that we have the spotter buoys. But if we look at the comparison with the model, they are also very good. So we're quite confident with the comparison, but because there's none of them is contradiction. Now we'll see the computation, because if we look at the buoy comparison with the buoys, we cannot draw the conclusion which one shall we choose, whether ST4 or ST6. If we look at the computational time, so this model was run at the Pegasus using the 160 cores, and the total number of CPU hours we use for ST4 is 47,000, more than 47,000 hours, CPU hours. And then ST6 35,000, more than 35,000. That actually means that ST4 runs slower than ST6. If we look at the our simulation for 2 years, we can see that every month simulations for ST6 is lower than 1600 CPU hours, while the ST4 have all above 1800 CPU hours. What's actually the point of this? If we assume that we pay the cluster, and then the cost of the cluster is about 5 cents per CPU hours, that means that the cost for running the ST4 is more than $2,000, while the cost for running ST6 is less than $2,000. But it's not quite significant because it's only different $600. Might not be very significant. But it's quite significant if one is interested in high costs. High costs, for example, one wants to study the wave climatologies or wave trend or wave energy, and then they would be significant. For example, for the high cost 30 years, if you run the model for this setup for 30 years, and then we can see that ST4 will cost more than $35,000, while ST6 will cost only $26,000. So yeah, little bit, almost $10,000 difference, which is for me is quite huge. Okay, now that's a computational time, so we can choose which one we can use. So if we believe that what we have done, if we trust the statistics, and then the real significant wave height around Monterey Bay in 2021 in October will be like this. Now let's see the mean seasonal. So which months in which season in Monterey Bay with significant wave height is very high. So we see the winter is quite high, but in spring it's much higher. And if we look at the summer is very cold, and then autumn is starting to increase. We also see the mean significant wave height for 2 years, and we can see that significant wave height during this winter and spring are above mean significant wave height, while during the summer and autumn we can see that below significant wave height. We also check the standard deviation to make sure that we there's nothing a species in the model, or there's nothing sudden change, so we check. But we look at the standard deviation, so they're all very good. And then we look at the monthly mean. So we started from January until December, but for simplicity we only take the January, March, and May, and so you can see that in May is very high, significant, very high. So next month will be very significant. Well, the July until September is very quite calm. So that's main significant wave heights. And now we can see the the question is where the waves in Monterey Bay are coming from. We can see, we check from the NDBC, and also, and then we compare the model. So if you look at this is the wind from, so wind speed, wind direction I mean, and with wind speed. So it's as we can see that the wind direction, wind is mostly coming from northwest. And if you look at the wave directions, they are also coming from, mostly coming from the northwest. We select 3 different buoys, and then they are all very consistent that the wind in Monterey Bay are mostly coming from northwest. And also the waves are also coming from that. What about the model? The model, we compare the model with the buoy, and then they are all similar. So, well, how do we compare in precisely? Well, we need to compare using the statistic again. But in general, we just saw that the directions of the wave based on the buoy and the model are similar. So that's wave directions, and then the last topic I'm going to share is sea and swell. So if you like surfing, so you will know when the right time to go for surfing in Monterey Bay. So what's actually the wind? The wind waves. So wind waves, then the swell. So wind waves generated by the local wind, while the swell also generated by a wind, but it's very far away. For example, if there is a storm in Alaska, or there is a storm in close to Japan or southern hemisphere, and then they will propagate through the Pacific. And then the wavelength for swell is much longer than the sea, and the period also is much longer than the sea, and also the swell is much more regular. Sea is quite irregular, and then so we can say that they're quite smooth for swell, while the sea is not really. So how do we relate this definition to our work? We take advantage of the period. So we are looking at 2 different cases. One case is we assume that if the less than 10 seconds, if the period less than 10 seconds, and then we assume that's wind waves, but longer than 10 seconds, we assume that they are swell. So that's the first case we do. And then, so we look at the spectrum. So we calculate the spectrum, the total energy of the spectrum which are less than 0.1 Hertz. And then we calculate also the total energy of the spectrum which are greater than 0.1 Hertz. And then we convert the total energy to the significant wave height using this formula. So we calculate all of these things, this spectrum, and then we calculate every hour, so each time step. Once we calculated all the time steps, and then we can get the significant wave height. So on the top is the significant wave height for the frequency less than 0.1 Hertz that we assume that would be the swell, while in the middle is the significant wave height in which the frequency greater than 0.1 and then we assume that's a wind waves. So if we look at the swell, so it's, swell in Monterey Bay around the summer is very calm. So as you can see from here. So if we look at the spectrum, so I've just selected 2 different times, and then we can see here that this is the swell dominant and this is the wind waves dominant. If we look at the buoy, we selected one buoy, and then we compare the model with the buoy. As you can see here that the buoy and the model are almost overlapped. So we can actually see the and this is actually different buoy with the previous one, and we can see the during the summer in Monterey Bay, swell is very calm. I mean, it's not really significant, so we cannot go for surfing in summer. I'll show you later where to go surfing in summer. And then the first case we divided the spectrum into 2 different parts. Now we divided it 4 different parts because we assumed that at the beginning we assumed 0.1 Earth is a swell, and then now we divided to 4 different partitions, and then we follow the same procedure. We calculate the total energy of the spectrum, and then we convert it to a significant wave height, and then we can get this significant wave height that's based on the spectrum partitions. So we can see these figures definitely show the wind waves with less than 2 meters, less than 2 meters. Now we compare this result with the buoy as well, but instead of comparing the time series, which is difficult to draw the conclusions, we do the similar with the buoys. So as you can see here, this is for the frequency less than 0.06, and then this one is between 0.06 to 0.09, and they are all very similar in statistics. The most interesting result here is the wind speed, wind waves. Wind waves between ST4 and ST6 are exactly the same. So almost exactly the same. This using a NDBC buoys. But for less than 0.2 Hertz, sometimes the ST buoy is good, sometimes ST6 is good. But the interesting thing is for wind waves, they are all the same. And then we change the buoys. We use the CD buoys. So they have the same result, similar result. I mean, if the wind, we can see that here the wind waves, they are exactly the same for RMSE. All the statistics showing very good agreement between ST4 and ST6. So this is a very interesting result. Well, fortunately, we haven't done for the CLASI buoys. Now, what we are going to do next? We're going to do next is we are going to looking for the swell directions, meaning that the swell in where the swell in Monterey Bay, where the swell are coming from. That's we are going to look at that, and then we also need to look at the original of the swell, whether they are coming from Alaska or coming from Pacific or coming from the southern hemisphere. So that's what we're going to do next. So this let me draw a summary here. That so based on the statistics, what we can say that ST6 is good in is good in fluorescent coefficients, but lower scatter index. But ST6 is lower RMSE and the bias. And then ST4 runs lower Then ST6, this is particularly significant for hindcast. And then in Monterey Bay, wind and waves are mostly coming from northwest direction. And then we can see that the swell activity is generally low intensity during the summer. So meaning that we cannot go to go surfing in Monterey Bay in summer. So during the summer you can probably go to Indonesia for surfing. We have the swell from southern hemisphere, which is very significant. And then both ST4 and ST6 perform effectively in swell conditions. So we can see the wind speed. They are very good. I mean they perform the same. Before and I close this talk, let me thank to the University of Miami, Rasmus, and both Department of Pearson to having me here for almost 6 months, especially for Professor Brian. Thank you for the time and also the support during my stay. Yeah, so this is my final week at the University of Miami. And then my university in Indonesia, and one good thing of my university is they always support us to work together with other people or visit other people, because we know that the world is too big to be treated alone, so we need the collaborations, work together. And then my sponsor, my sponsors, without the sponsor I probably couldn't come to US, especially in UN. And so I'm here sponsored by Fulbright. And also IIE, Institute of International Education. So this IIE looks after all the Fulbright students here, or Fulbright scholars. And then last but not least, AMINEF. AMINEF is American Indonesian Exchange Foundations. So this AMINEF manages all the Fulbright program in Indonesia. So if we want to apply for Fulbright scholarship or Fulbright scholar, and then we will go to the AMINEF. They are very helpful. They will manage everything. They will just submit their documents and they will process. They will proceed the documents or from application form, visa, and the ticket. They will manage. All right, thank you very much for that, and then I'll turn back to Ron.
Yeah, thank you very much for the nice presentation. Do we have questions from our audience here?
I have a question.
Yes. Sanjeet.
Thank you for the talk. There was one PowerPoint in which you showed the differences in computation time between the ST4 and the ST6, and then it kind of showed that like how the timings were. That was this one. So it's like, so it shows that like how the CPU time is changing with the time as well, like from like January 21 to January 23. So like why the time is changing, like because there is more data that is being processed.
Why? Because the model runs every month. So
I know. For example, say like the computer, like the CPU time.
This one?
Change,
they are changing.
Yeah.
Well,
from month to month.
Depends on. I think it depends on the node that they used by the supercomputer. But also because if we see let's say in February, this is February, because so we cannot have the same time, because let's say January until 31 days, while February is only 28. So different 3 days, there would be different computational time. Yeah, I'll look at that as well. But so they are not exactly the same. Let's say May, April, and May, different 1 day. They will be different.
Yeah, for example, like the 5th node.
This one is and it is quite unusual for this for ST4, but yeah.
Because I thought that there is more data that is processing, but then that is
No. I'm not sure why this slowing down.
Okay.
But this time obtained from the reported by the supercomputer, so we don't calculate it manually.
So this is something that they just give you, like it's something.
Yeah, Pegasus reported the time. So once the job completed, and they will follow with their the report that's saying that this has used CPU hours and then memory. So very details there.
Okay, thank you.
Yeah.
Could it be possible that some computations become more time consuming if there are some special conditions where the resolution of the model, the time resolution has to change, or it has to go through some extra loops of computation because some needs more resolution somewhere, or something more complicated needs to be integrated, depending on the wind conditions or something like that?
Well, indeed, it depends on the time step, but in this case, we apply the same time step. So that there's no.
So it should be exactly the same amount of computations from time step to time step.
They're exactly the same time step from one computation to different computation. But there's we the supercomputer use them at not randomly, so we cannot manage them.
More questions? Yes.
We have one person in Zoom, but I mean, this is enough.
Thanks for the nice presentation. So I'm just curious, how can the current
Say again? I didn't hear.
Did you include surface current in the model? Was surface currents included? Or?
So what?
Surface currents, were they included?
No, we don't include current.
is the matters? I mean, its current matters a lot.
No, we don't include current. So we only apply the wind. Is that what you mean? Yeah.
So
Because the reason is we are told that it's okay. So the reason is we don't think that current is very significant in Monterey Bay. Yeah. So we don't include it.
Okay. Any further questions or comments? Pearson?
Hi, Agustinus. How did you deal with the bottom friction for ST4 and 6?
Say again?
How did you deal with the bottom friction for ST4?
Bottom frictions, we assume that they are ascending, so both of them use that's what we call it, the ascending SOX bottom frictions. So they have all the formula for SOX bottom frictions. We assume that they have ascending. Otherwise, they will use the Jones one.
So there is
bottom friction.
the same for both switches.
Yes, we apply both.
Anything else to discuss? If not, thank you again for the nice presentation. Thank you all for coming despite the competition from the solar eclipse outside. And come again on Wednesday morning when we have another OCE faculty candidate seminar, or on Wednesday afternoon when we have another 1 hour student seminar, or on Thursday afternoon when we have another ATM faculty candidate, or on Friday morning when we have 3 more 15-minute student seminars. And ideally you come to all of them. Goodbye.